Hello folks, day 1 of Unit 7. Going to be looking at inverse trig, vectors, and applications of trig. So let's think real quick about how inverses work. The big idea is swap x and y and then solve for y, and you have yourself an inverse function. So first thing we need to do is subtract 3 from both sides. And now we have the square root of 2y, so to get rid of that square root, we need to square both sides. So we get x minus 3 quantity squared equals 2y. Last thing we need to do is just divide by y. So we get y equals x minus 3 quantity squared over 2. Next problem, same idea. We're going to swap x and y. So x equals 3 times y minus 4 quantity to the power of 1/3. Well, remember that a 1/3 exponent is the same as a cube root, so we're going to need to cube that to undo it, but first we need to get that side by itself, so divide by 3 on both sides to get y minus 4 to the 1/3. Now we can cube both sides to get x over 3 quantity cubed equals y minus 4. And then lastly, add 4 to both sides to get x over 3 quantity cubed plus 4 equals y, the inverse function. Okay, last problem, same exact idea. X equals 2 log base 3 of x plus 1. Let's get that log function by itself, so we'll get x over 2 equals log base 3 of x plus 1. Now this is where we need to take the log and rewrite it in exponential form. So to do that, we will get 3 to the power of x over 2 equals whatever's inside the log. I goofed up. I should have written y inside there when we switched x and y, because that should give me y plus 1 over here. And so the final thing we'll do is subtract 1 to get y equals 3 to the power of x over 2 minus 1. So big idea with all of these functions is that we had something stuck inside of the function. We had a variable that we wanted to get out, and in order to get that out, we needed to use inverse functions, the undoers. We're going to do the same exact thing with trig functions today. We want to get those theta values out of the function, and to do that, we need inverse trig. So let's think real quick about the horizontal line test and what it tells us. You may remember the vertical line test if you have some relation and you want to determine if it is a function or not. You can give it the old vertical line test, and how it works is draw a line, a vertical line, through your graph. If it intersects at more than one spot, then your relation is not a function, because for a relation to be a function, every x value can only have a single y value. And that one right there with that blue line has 3. Now, why do we care about the horizontal line test? Well, the horizontal line test tells us the same thing, but for that function or relation's inverse. Since this is intersecting that graph at 3 spots, that's telling us that the inverse of this green function is not itself a function. Well, why are we interested in that? Well, think about the sine function. I could draw a horizontal line anywhere through there, and I would intersect at many, many points. And if I'm thinking about negative infinity to infinity, I would intersect at infinitely many points. And that's a problem. Clearly, the inverse here would not be a function. So what we need to do is we need to restrict our domain. And what that means is we're going to focus only on a small portion of the graph, and that will be our definition of where the function is defined. What we want to do is look for a section that is continuous. We want to hit every single y value of this graph, and we don't want to repeat any y values because then it would fail the horizontal line test. And the interval that makes the most sense to do this with is between negative pi over 2 and positive pi over 2. And think about why that is. I could do the same thing between pi over 2 and 3 pi over 2 like that. I don't repeat any y values, so I will pass the horizontal line test, but the problem is we want to start centered on that origin right there. And so we're defining it from -pi/2 to pi over 2. A couple implications of this that are super important. If you think of this function, we want to not think of sine of x, but we want to think of y equals sine inverse of x, which is also written equivalently as arc sine of x. Now we need to think about the domain and the range of this inverse function. And keep in mind that it will be flipped from whatever the domain and range is for sine of x with this restricted domain. So let's think about the domain of arc sine of x, or of sine inverse of x. Again, they are equivalent. Well, the domain is going to be the range of the sine function. And the range of the sine function, remember range is y values, the range here goes from -1 up to +1. And then if we want the range of the inverse function, we need to think of the domain of this original function, with which we have restricted to -pi/2 and pi over 2. This has some implications that are important to think about. This means that since our domain is -1 to 1, the only values you can put into the arcsine function are numbers between -1 and +1. So if you see something like arcsine of 5, you automatically know that that will be undefined because that is not in our domain. Other implication of this, if you think about the range right there, that is saying those are the only possible outcomes, -pi/2 to pi/2, which means we're looking only at this half of the unit circle, from pi/2 up here down to what we will now call -pi/2, which you might be more familiar as 3pi/2. But that means if you're dealing with an angle down here, like say 11pi/6, we will no longer be referring to that as 11pi/6, but rather -pi/6. So although that's slightly different, it might actually make it a little easier to refer to that angle. But what about the arc cosine function? If we have that same restricted domain between -pi/2 and +pi/2, well, think about what happens. Horizontal line test says that is not a function, and so the inverse is not a function. And so we need to look at a different restriction, and we will look between 0 and pi. Again, that's the most natural domain we could choose for this. We hit our +1 maximum value all the way down to our -1 minimum value. So again, the domain here will also be -1 to +1. The range, we are now going between 0 and pi. So very similar to the sine function, but looking at a slightly different output, 0 to pi instead of -pi/2 to pi/2, but it's got the same domain. So that's nice. Last one to think about is tangent. And again, think about what we're looking for. We want to hit all of the values. We don't want to repeat anything, and we don't want to have any discontinuities, which means we're going to look between -pi/2 and +pi/2, which are the asymptotes of the function. So again, let's think about the domain of this function. This time, if you think about that tangent function right there, that green function, between -pi/2 and pi/2, that green function, since it's continuing on forever towards infinity and -infinity for y values, that means that our domain now is all real numbers. You can input any value and you will always get an answer. So that is different than arc cosine and arc sine. And what about the range? Well, the range is between -pi/2 and pi/2, just like sine, because they are both odd functions. But this time, we will not include -pi/2 or pi/2 in the output because the tangent function is undefined at those values. So let's think about how this is going to work. The other day we were looking at problems last unit like this: 2 sine theta minus √3 equals 0. And what do? Well, we solved for the trig function. Sine theta equals square root of 3 over 2. And we thought of this as the question, what angle in radians gives us a sine value of the square root of 3 over 2. Well, that's exactly what these inverse functions are doing. If I took the inverse sign on both sides, well, what would happen on the left? I've got sine inverse of sine. Those are inverses of each other. They undo each other, so we're left with theta equals, on the right, sine inverse of the square root of 3 over 2. So really, we were kind of doing inverses already. We just now need to think of this with a restricted domain. So remember, sine function is going to be between pi over 2 and negative pi over 2. And we want to know what angle gives us a positive square root of 3 over 2 for the sine function. Well, that's going to happen right up here at pi over 3. Think about last unit. We also would have included 2 pi over 3 as an answer, but that is not in our range for the inverse sine function, and so it is not a solution. So now let's just run through a few of these and make sure we're feeling okay with it. Arc sine of negative 1/2. Remember, sine is using this half of the unit circle, and we want to know where is the value of sine equal to negative 1/2. Well, I always think of positive values first. I know that sine of pi over 6 is a positive 1/2, so that tells me that negative pi over 6 would give me a sine value of negative 1/2. So that's my answer for the first one. Second one, inverse sine is the same as arc sine, and again, it's asking what angle gives me a root 3 over 2. Well, we actually just did that right there. We get positive pi over 3. That angle right there. Now, sine inverse of 2 is undefined because our domain is negative 1 to positive 1. And so that is undefined. We're putting in a number that this function cannot handle. But again, think about why that's happening. That's happening because the sine function goes between positive 1 and negative 1. It never hits the y value of 2, hence inverse sine of 2 is undefined. Okay, cosine. Cosine. Remember, this now has a range between 0 and pi. So we're only looking at the top half of the unit circle right there. We've got root 2 over 2. Where does that happen? Well, that happens at the pi over 4 values, and root 2 over 2 is positive here, so we get a positive pi over 4. Where is the value of cosine negative 1? Well, that's happening over here at pi. Where is the value of tangent 0? Remember, tangent has the same domain. Inverse tangent has the same domain as inverse sine. Goes between negative pi over 2 and pi over 2. But where is the tangent 0? Well, remember, tangent is slope. Slope of a horizontal line is 0, and so we just get 0 as our solution. Last one, where is the tangent value negative 1? Well, hopefully by now we know that's going to happen at what this would have been called 7 pi over 4, which we are now calling negative pi over 4. So that is the basics of using these inverse functions. Again, it's coming down to a knowledge of the unit circle.